Okay, hello there, Cappuccino. I promised I would make a helper video for page 366. And I have to say, the questions here are not very well written. And in fact, the publisher didn't think they were very well written, and they changed them between the time that they printed the book and they released the digital copy. So problem number 1 is a perfect example of that. In the book, it's completely different than on the digital page. Well, not completely different. Same information, but asked in a really different way. So regardless of whether you're looking at the digital or the printed textbook, they do give you the same information. So it says we have 2 AC electrical sources, each output a maximum of 110 volts and have a phase difference of 60. So when we have electrical outputs, voltage functions, they are written as sine functions. So for problem number 1, we know we have 2 of these. So voltage number 1 and voltage number 2, we know that they both have a maximum output of 110. That is our amplitude, okay? So they're both going to have 110, and then we're going to have the sine, and it doesn't matter what the period is because they're going to have the same period. They don't tell us they don't, and we don't know how to solve problems that don't have the same period. So we're always going to assume they have the same period. And I notice my pencil is not showing up very good. So let me go over this in pen. 110 sine and theta, and the other one, 110 sine theta. It could be some number times theta. It doesn't matter as long as they're multiplied by the same number. So we'll just ignore if there's something happening there. And it says that they have a phase difference of 60 degrees. So one of them is moved 60 degrees relative to the other. So we're just going to assume one of them is starting at 0 and the other one has a phase difference of 60. So it doesn't matter if it's to the right or to the left, just that the difference is 60. That's all that matters. So this would be like theta plus 0, and this is theta plus 60. The difference between the two, the phase shift is 60. Righty. So then we want to know what is going to be their combined output. So if you're looking at the textbook, it tells us the answer. It's a show that problem. So we know the answer is going to be 110 root 3, but now we have to figure out how to get it. So what happens here is you can treat sine functions just like we treat imaginary numbers. And I had a dream about this the other night. Oh my God, I've been doing so much work on complex numbers that I was actually dreaming about it. So just to go over what happened in my dream, which is totally bizarre. You know, if we had like 110 cis theta, and let's say theta in this case is going to be, it's going to be the 60 degrees, okay? The cis, remember that stands for cosine of theta, whatever this angle is, plus I times the sine of this angle. And we get that from our use with vectors, right? If we have a vector going like this and we want to write its coordinates here, we can figure out what x is and what y is if we know this angle by using sine and cosine. If we have the amplitude, which here we know is 110, if we have the amplitude and we have the angle, we can figure out what x and y is by using cosine for x and sine for y. And so notice when you're doing a sine function, we only care about the height. We only care about sine. And so it's just this part. So that's why we can change 110 sine theta into 110 cis 60, because we really don't care about the cosine part. Really, this is just the imaginary part of our function. It's 110 times the imaginary part minus the I. So anyway, I digress. We don't even need to go over that. But I had a dream about this, and it all became clear to me. It's like, oh, the sine function is just the imaginary part, because all we care about is the y value as we move our way around our unit circle. So anyway, I digress. Back to pen, because this is what we care about. So we want to know what is the combined voltage. So we want to add 1 plus 2, the voltages of 1 plus 2. So 110 sine theta plus 110 sine theta plus 60. And the way we do this is This is basically polar coordinates. If we think about our complex numbers, these are polar coordinates. That's a pain to add them together. The easiest way to add complex numbers is to change them to rectangular or Cartesian form. So that's what we're going to do. We're going to change these to rectangular or Cartesian form. So if I rewrite this one, I should have done this earlier, darn it. This is the same as theta plus 0. Okay, get rid of that. That's the same as theta plus 0. So if I change this to cis form, which is going to help me change them to Cartesian form, I'm going to have cis 0, because it's theta plus 0, plus 110 cis 60. Okay, so we can just, this is just like what we can do. It's an application of complex numbers. When you take electrical engineering in college, you can get more into the weeds about why we're allowed to do that. But again, I was just trying to show you, it's basically, we're just talking about the imaginary part. So anyway, onward we go. So now I want to change this to Cartesian form. Super easy to change it to Cartesian form by just writing out what does cis mean. It means cosine of the angle plus I times sine of the angle. Okay, ooh, I almost put theta, but that's not it. Okay, and then the other one is 110 times cosine of 60 plus I times sine of 60. So we're changing this to our rectangular coordinates. So let's go ahead and figure this out. Cosine of 0, okay, back to our unit circle. Cosine of 0, 0 is right here. Cosine is 1. So I have 110 times 1 plus I times sine of 0. Well, sine is 0. And then the other one, 110 times cosine is 60. Okay, 60 is pi over 3. That would be right here. This would be 1/2 root 3 over 2. So cosine is 1/2. So I have 110 times 1/2 plus I times sine of 60. Sine is root 3 over 2. Okay, and now I can simplify this. 100 times 1 is 110. 110 times 0, I is just 0, so that one goes away. And then over here, 110 times 1/2, well, that's 55. Plus, and now I got to multiply this one out. I have I times 110 root 3 over 2. Okay, so if I simplify that, I can add these together, add the real parts, my complex numbers. 110 plus 55 is 165 plus I 110 root 3 over 2. And I could reduce that, actually. Why don't I go ahead and do that? 165 plus 55 root 3, that's times I. All right, so now I changed both of my sine functions. I changed them to cis, polar coordinate form. Then I took my polar coordinate form and I transformed it into rectangular forms. Here they are right here. This is voltage 1, and this is voltage 2. And then I added those together, and here is the combined. But it's in rectangular form, and so in order to see what the combined voltage is, I need to find its magnitude and change it back to sine form. So in order to do that, I'm going to change it back to polar form. So to change this to polar form, I need to find its magnitude. And really, that's all we care about for this problem, because it just wants to know the voltage, and the voltage is in front here. So I'm going to find the magnitude of this. So my magnitude is going to be the square root of 165 squared plus 55 root 3, the whole quantity squared. And if we do that on our handy dandy calculator, oh, what do we get? Here we have it. Okay, if you do that on your calculator, you get the square root of 36300, 36,300. And I notice those can all be divided by 3. So I'm going to change that to 3 times 12100, 12,100. And then, 121, that's 11 times 11. And then there's a 0. So this is just going to be equal to 110 times 110, because 11 times 11 is 121, 0 times 0 is the 0, 0. And now I can simplify that to 110 square root of 3. So all I needed to do was find the magnitude. I don't need to find the phase shift for the resultant voltage. I just needed to find the magnitude. And there it is. All right, awful lot.